we are going to solve a particular problem using a mathematical computations and a simulation. So for this problem, a single-phase bridge rectifier has an RL load with R or resistance is equals to 10 ohms and an inductance equals to 25 millihenries. The AC source is Vs or known as Vs equal to 170 sine 377 volts. Determine the average and RMS currents in the load and in each diode. So for this problem, we have the maximum voltage or the peak voltage that is equal to 170 volts since this uh, form means that 170 is the maximum value or the peak value and the 377 is equals to 2 pi f, which it will indicate its frequency. So our resistance is equals to 10 ohms and our inductance is equals to 25 millihenries. So to solve this problem, we should determine what is the output current or the average current for the load. So to solve that for that, we should solve for the average voltage, which is equals to 2 times the peak value over pi. By substituting its value, we can get 108.2254 volts. And the formula for the current is voltage out or average voltage divided by R. So by substituting its values, which is the 108 volts divided by 10 ohms, is equal to 10.8225 amperes, which this will serve as the average current for the load. Next is we're going to determine the root mean squared or the RMS value or also known as the effective value of the current. So first, we should let n is a harmonic number. So the formula, we should determine its voltage in its harmonics. Since we are dealing with the single phase bridge rectifier, so Vn is equals to 2 times the peak value over pi times the quantity of 1 over n minus 1 minus 1 over n plus 1. So we consider the for this solution, we consider the second harmonic and the fourth harmonic. So for the second harmonic, we substitute n equals to 2. So by substituting its values, we get the value of 72.15 volts. Now we will solve for the value of the fourth harmonic by substituting its values again, where n is equals to 4, we can obtain, sorry for the typographical error, obtain the voltage of the fourth harmonic equal to 14.43 volts. So next, we are going to compute for its impedance. The formula for the impedance is Zn is equal to square root of R squared plus N times omega L. in which it has the form of R plus J and omega L. To obtain its magnitude, since we are going to deal with the magnitude, we should square R and W L squared, and then the sum should be it will be square root. So we will square root the sum of the squares of the two quantities. So for the impedance of the second harmonic, by substituting its values, we can obtain the value of 21.34 ohms. The value of impedance is ohms. So for the fourth harmonic, by substituting its values where n is equals to 4, we can obtain the impedance of fourth harmonic equal to 39 ohms. Next, we are going to uh, determine the values of the current in the second and fourth harmonic. So, to do that, the nth harmonic, the current of the nth harmonic is equal to the voltage of the nth harmonic over the impedance of the nth harmonic. So for the second harmonic, the current of the second harmonic is 72.15 divided by 21.34. So we can obtain the value of 3.381 amperes. And for the fourth harmonic, so we should substitute it for V4, which is 14.43, and the Z4, which is equal to 39. By computing it, it will obtain the value of 0.37 amperes. To determine for the RMS, which are we're looking for, we should square root the sum of the squares of the average current of I2 over square root of 2 and the square of I4 over square root of 2. Substituting its values, and we can obtain the value of 11.0865 amperes as the RMS value of the load. Now, to determine the average current for each diode, so we should divide the average current of the load by 2. So 10.8225 over 2, we can obtain the value of 5.4113 amperes. So this is the same as earlier. It is become doubled, but for the RMS value, we it has the formula of the RMS value of the load divided by square root of 2. So by substituting its value 11.0865 divided by square root of 2, we can obtain the value of 7.8393 amperes as the RMS value for each diode. We are going to create a new project. So we will name it as summative 4. Then click OK and select Create Blank Project. So as you can see, there is a new canvas in which we can create our circuit. So let's go to place, PSpice component, and let's add our diode. Since it is a bridge rectifier diode, we should add 4 diodes. So there, as we can see, the 4 diodes are already added. Now, we should add our resistor and our inductor by going to PSpice component, then passives, select R and L for resistor and inductor respectively. So this is the resistor, going to place and clicking the L for the inductor. So let's delete the other one and let's move this one. There. So and next, and we should add our voltage source by going to place, PSpice component, source, voltage sources, and select sign here. Then we will add our ground by pressing G. Then click OK. So the only thing we need to do is to connect these components to each other. So since it is a bridge rectifier, each diode is connected to each other. So here and there. So to add wires, we should press W. So let's try press W and then go to and then connect the resistor and the inductor. So there. And this end of the inductor is connected to this end. So by pressing W, press the end of the inductor, rotate, and then click to cut or to enable rotation, and then click it here. So we now already connected the other end of the inductor to the other side of the bridge rectifier. And now we are going to connect our AC supply. So pressing the W, we will connect the supply here and on to the other side, which is here. So let's try this one. Let's delete this node. And let's try to connect this end. let's try to delete this one. Let's make sure that we should uh, connect our wires properly to avoid any errors in terms of simulating the circuit. So there, everything is connected to our circuit. So let's change the values or edit the values of our resistor, inductor, and for our voltage source. So for our resistor, we should change it to 10 since it is stated in the problem that the resistor is equal to 10 and the inductor should be equal to 25 millihenries. And then for the V off, it should be 0. The V amplitude should be 170 since 170 indicates the peak value. And for the frequency, we should solve using by deriving the formula where omega is equals to 2 pi f or f is equals to omega over 2 pi. By solving it, as we can see on our calculator, 377 divided by 2 times pi is around 60 hertz. So we will type here 60. And for the AC, it's 0. So now the values is set, we can create a new PICE or simulation profile. So new simulation profile and name it as Summative 4. Then click create. So a new dialog box came in, and then for the runtime it should be 33. It should be 33.34, which means twice the period or 2 periods, milliseconds, and it will start saving by 16.67 milliseconds. And its maximum step size is 10 microseconds. So we will click OK. So now let's run our simulation. So as we can see, there is a new window. Let's right click, then add traces, then click average. Let's plot the load current first, which is the average load current and the RMS load current. So IR1, then click OK. And next one, let's add the trace of the RMS value of the load current. So let's try to measure this too. As we can see, the values obtained is around 10.434 for the average current, and the RMS current is around 10.705. By looking to our solved problem, which is here, Our average current is 10.8225 amperes. So, by computing its percentage difference, it should be the absolute value of 10 point. So let's try it again. Absolute value of, let's try. So 10.434 minus 10.8225. So it equal to 0.3885 divided by 10.8225 times 100. So it is about around 3% error. By obtaining its absolute value, it's about 3.59% as their percent error for the average current. Let's try to compute for the percent difference for the RMS. On our computed version, it is around 11.0865. So let's try it here. So 10.705 minus 11.0865 divided by 11.0865 multiplied by 100. This will equal to around 3.44% as a percentage difference of the simulation and its computed value, neglecting the negative sign on the computation since we obtain the absolute value of the difference in our numerator. So as we can see, it is very small and it is accepted since it is below 5%. So how about for the current in each diode? To do that, we should delete our traces first. Then we will add a new traces. So as we can see, the formula for the average current is average current of the load divided by 2. So average of IR1 divided by 2. And then click OK. And now for the RMS value, we should add another trace. So RMS of the IR1 divided by square root of 2. So let's try to measure this 2 with our cursor. So as we can see, the average current has around 5.2168 amperes, and the RMS value of the diode has a value of 7.57 amperes. So let's try to compute its difference again. So for our computed value for the average is 5.4113. So let's try to compute. So as we can see, 5.2168 minus 5.4113 divided by 5.4113 times 100. This around, by neglecting the negative sign, it has around 3.59% of percentage difference. So the difference of the two values is around 3.59%. So let's try to compute the percentage difference for the RMS value. So as we can see, the RMS value computed is 7.8393, and the simulated value has a value of 7.57. So 7.57 minus 7.3893 divided by 7.3893, since this is the computed value, multiplied by 100. So as we can see, the percentage difference of the two values is around 2.44 or 2.45%. It is lower than the computed average for the computed percentage difference for the average value than the RMS. So this means that the values obtained in our simulation is correct, and our computed value is correct. It means that the two values are matched since the percent difference of the two is less than 5% or smaller. So hope you like this video and see you again next time.